All right, lecture 7, video 7. Today we'll be talking about LQR and LQG. And I'm here in VS Code, and I'm gonna get right into it by loading the control system package, linear algebra, and plots. And we'll start by defining a system P. It's a simple double integrator in discrete time, so we have two states and a single output. And the output here corresponds to the position of the double integrator. So maybe we are interested in designing an LQR controller, and we do that using the familiar LQR command. We define two penalty matrices that belong to the cost function. So we see we have the cost function here. We penalize the square deviation of the states and the square control effort. And here I just say that these two are identity matrices. And then that gives us a state feedback gain L that we can multiply our states to produce our control signal. So if we want to simulate that, we can do that by providing a function u to the function LSIM. Here, u is allowed to be a function of the state and of time. And in this case, it's just a negative state feedback with our state feedback gain L. I define a vector of time points. An initial condition is just 1, 0. And I call LSIM with that initial condition. Here we see I provide 3 positional arguments, p, u, and t. And then I have a semicolon, and then I provide x0. That's because x0 is a keyword argument. But it happens to have exactly the same name as my variables. I could have written this, but since the variable have the same name, it's fine to just write x0. That gives me a result, which is of type sim result, and that's something that can be plotted immediately here. So I do that, and we have position to the left and velocity to the right. And we see that our position converges down to 0 error here. And in the call to plot here, I said plot y false. So by default, when you plot the simulation result, we only plot the output. But instead I say plot x true. And that's because I want to plot both position and velocity, but I only have position as output. And I say layout 2, so I get 2 plots instead of both traces in the same plot. So in this case, I simulated the system using the function here, u. But I can also create an explicit controller. And I do that by just passing my gain matrix into a state space object. So that creates a state space object with a static gain. It only has a D matrix. Everything else is 0. So I can do that. And then to form the feedback loop, I create a new system here. And the only difference is that instead of my output matrix C, I pass the identity matrix. And that's how I can form the feedback interconnection, because state feedback assumes that you have access to all the states. And as you see here, I is just a uniform scaling. It doesn't have any size, but the SS function understands which size it should give the C matrix here. So in this case, it creates a 2x2 identity matrix for C. And it's okay to pass just a 0 for the D matrix, then the D will have the appropriate size. So I can create those two, and then I can create the closed loop system from kind of references to outputs by using the feedback function. And then I can call LSIM with this state feedback closed loop system. And in this case, I pass a function that only inputs zeros as the reference to this simulation. And I plotted that on top of the previous plot, and we see that they are exactly identical in this case. But right now we have assumed that we can access the states, and that's usually unreasonable. We can almost never measure all the states, and even if we can measure the states, they are associated with some measurement noise. So in general, we like to design some kind of observer, and in this case we will design a Kalman filter, or rather a steady state Kalman filter. And for that we need covariance matrices. We need one for the noise acting on the state and one for the noise acting on the measurement signal. And in this case I'm not going to tune that, I just provide identity matrices. I call the function Kalman. That gives me a gain matrix, and that multiplies my measurements to form an estimate of the states. And I can create now the full closed loop system using this little formula here. And that is sometimes a bit of a mess to remember. You can look it up in a book, right? But that gives us a closed loop system. But if we, that gives us the controller associated with the LQG controller. But if we don't remember this formula and we don't have a book at hand, we can just call the function observer controller. And that function takes the system, the state feedback gain, and the Kalman gain here. And it produces the same controller in this case. And then I can form a closed loop system using the feedback function, and I can simulate it. In this case, we see that we get a position trace here, and it looks slightly different. It's slightly worse. And the reason is, of course, that now we have an observer that must converge in the state estimate before it can do a good job controlling the system. So we get a slightly worse response here compared to the full state feedback case, and that's expected. And as you see, we only got a position trace. We didn't get a velocity trace, and that's because we didn't output the velocity from the system in this case. We only outputted the position. If we would like to add an output corresponding to the velocity also, we could do that using the add output function, and we can provide a row for the C matrix. So if we do that, we now have velocities also, and we can plot that, and now we get the velocity output here as well. All right, let's clear the plots and move on. So right now we have used the low-level functions LQR and Kalman, and we have assembled the controller, and we have assembled a closed loop system and simulated that, and all that's all fine. But if we load the package RobustAndOptimalControl, we have a type called LQGProblem, which does all of this for us. And that type expects something called an extended state space. And if I hover over that, we see some block diagrams, but I will actually move over to the documentation here and look at the documentation for extended state space. So extended in this case means that here we have our extended state space P, and it has two groups of outputs, Z and Y, and it has two groups of inputs, W and U. So Y are the outputs that we can measure, so our measurements, and U are the inputs that we can control, so our regular control signals. Z, on the other hand, is something we call the controlled outputs, or they are sometimes called performance outputs. So these are the outputs or some kind of fictional output that we are interested in controlling. And that may not be the same as Y. For instance, we might be able to control, to measure Y, but we're interested in controlling the velocity, and we don't have a measurement of that. But it might also be the same. We can just have the same output Z as we have U. And W here is some kind of external input, such as a disturbance or a reference. And the difference between W and U is that we cannot control W. It might be things like the sun is shining in through the window and heating up the room when you're trying to control the temperature. Or we also put references in this box here. So when we form the closed loop system using an extended state space, the controller here, K, in this block diagram, it only has access to Y. It doesn't have access to Z. And it can only act on the system through U, not through W. So W and Z are kind of fictional inputs and outputs or they are non-controllable and non-measurable. And once we have created such a system, there are lots of functions we can use on this more extended system. if we just pass a regular state space system into the constructor of extended state space, then we get the same output. So we get the same output matrix for Z and for Y, and the same for B, right? We get the same input matrix for W and U. But we can overload any of these matrices when we create this if we want to. So if we want to have exactly the same outputs, but we want to modify the inputs, we can provide just, this is called B1 and this is called B2 here in the constructor. All right, so I can create such a system. We see it here. We see that B1 and B2 are identical, the same for C1 and C2. And if I call LQGProblem now, LQGProblem wants the penalty matrices for the LQR problem and the covariance matrices for the Kalman filter. If I call that, we get the method error. And the reason I include this in the video is because method errors are very common in Julia, but they are nothing to be afraid of. Let's read what it says. It says there is no method matching LQGProblem with the number of arguments. And then it says that the closest candidates are, and here are 3 methods. So the problem here is that I passed in an extended state space as the first argument, and my second argument was a uniform scaling. So this Q1 is a uniform scaling. That's not a matrix. And we see that one of the closest candidates here, it expects an abstract matrix, so something that behaves like a matrix. And uniform scaling, it doesn't quite do that. For it to behave that way, we need to actually give it a size. So instead of just I write I of 2. And that gives me an actual matrix. So I do that for all of these matrices. And then we try one more time. And one more time we get an error. And here it says that the size of Q1 is determined by C1, not by the state, expected size 1. So what does that mean? If we look at our extended state space, we see that C1, we output a single output. But we provided a penalty matrix of size 2. So that corresponds to what we did up here and what we're used to maybe from very basic LQR design. But if we want to, so this corresponds to us penalizing both states equally. And if we want to do that, we need to say that the controlled outputs are both the states. So here I say that I am interested in controlling both position and velocity. And then at this, with a similar reasoning, I say here that I have noise acting on both states. So if we remember, B1 is the matrix that takes in, it's the input matrix for this noise input. And it tells the Kalman filter that there is Gaussian noise acting on both states if I provide the identity matrix here. So if I do that, we now see that B1 is an identity matrix, but B2 is the original B matrix. And then I can create my LQG problem. All right. And then there are lots of convenience functions defined for LQG. So you can just call observer controller on that, and you get the controller, which corresponds exactly to what we did up here, where we passed explicitly the system, the state feedback gain and the Kalman gain. That's all built into this. And we can see that it's identical to the COF is for output feedback. It's the controller I created above, and LQG is the controller I created now. They are equal. I can also ask what's the LQR gain of this LQG struct, and that's identical to the gain I computed by the explicit call to LQR here above. All right, and similar for the Kalman gain, they're also the same. So now I can create the closed loop system here with my LQG controller, and then I create a new plot here where I first plot the output feedback result from above, and then I plot the closed loop system response from my LQG controller created here. And we see that they overlap exactly. And then for advanced users, I include a last version here where I call LFT. That's short for linear fractional transform. That also produces the same result in this case. LFT in this case forms this system. So it closes the loop around K. And what K is built into the LQR struct. So it forms the closed loop transfer function from W to Z in this case. If you don't know what that means, that's okay. You don't need to know that to use the basic functionality here. But there are other nice convenience functions defined for this struct, this LQG problem. We can call gang of 4 plot, and we get the sensitivity functions here. Here I've modified the plot, so I put the legend in a particular place and I removed some labels. And here we see that we have a particular peak in the sensitivity function. Maybe this is a bit high. We also see that we fail to reject low frequency input disturbances, and that's because we don't have any integral action in this controller. And if you would like to add integral action, you can use the techniques from the previous video, from the pole placement video, where we augmented the system with the disturbance model. That works also here. But another way to do that is to use something called H2 design, and that's something we will have a look at in an upcoming video. That essentially, if H2 design and H infinity design are very similar, we create our weighting matrices and then we penalize certain sensitivity functions and so on. And by putting an integrator in one of the weighting matrices, we get the integral action. All right, so when I provided C1 is the identity matrix here. That means that when we solve the LQR problem, we penalize both states equally, in this case, since it was the identity matrix. Sometimes we're interested in penalizing maybe only outputs. We are not interested in penalizing the full state vector. And we can do that. And the way we do that is if we want to penalize the outputs, we have a single output, then we need to provide a Q1 matrix of size 1. And here I provide a covariance matrix R1, also size 1. So that corresponds to we have a single source of state noise acting on the system. And then when I create the state space system, I do not provide this C1 equal 1. Then C1 will default to the C matrix in this system P. So I could equally well have created the system like this. C1 is P.C. That will give me the same result. So that now indicates that my controlled outputs are the same as the measured outputs. If we do that and create the LQG problem again, we can create the gang of 4 plot, and this time we see that we have a much higher peak in sensitivity function, 2.5, and before we had 1.48. And the reason here is that if we perform state feedback on a double mass model of a double integrator model that has position and velocity, that corresponds exactly to a PD controller, proportional derivative. So we have one feedback element acting on the position and one on the velocity, and velocity of course is the derivative of the position, so that's a PD controller. If we only penalize deviations in the position, then instead of a PD controller we now have a P controller only. So this is in fact even though we use an LQG controller here, it corresponds exactly to a P controller. So that's of course not a particularly interesting controller, and that's also why we get some phase loss compared to before, and we see a much worse sensitivity function here. We can actually look at, for instance, the Nyquist plot. Let's see if I can spell. And we can do that using this loop transfer function that we had from before. Let's see if I recreate this thing. That gives me, maybe that's a bit hard to read. Let's see if we set the x limits. Let's bound it to -5 and 1. All right. So we see that our original LQG problem controller that included a penalty on the velocity, it gave us this Nyquist curve. But if we now do the same thing for this, let's change this to add number 2 so we don't overwrite everything. Sorry for this little mess. All right. Then we add to the previous plot, like so. Yeah, of course I need to compute the observer controller. We now see that the Nyquist plot is much closer to the critical point in this case, and that is why we have a much higher peak in the sensitivity function. All right, so this was a basic LQR, LQG workflow. And if you're interested in learning about more advanced workflows using this, I suggest reading the tutorial in the Robust and Optimal Control documentation called LQG Control with Integral Action. That performs this disturbance model augmentation to achieve integral action. And we also have H2 design tutorials, but that's something we will cover in the next video. All right, thank you for today.